Okay. Let's go from current slide. Everything's really slow today. All right, let's hit a couple of issues here. Okay. First, I think I've already asked you this. I think I know the answer. Have you done the shooter course evaluation? I knew that. Okay, I'm doing it mostly. Okay, so it can be recorded. All right. Secondly, I've returned all your papers to you, except the determinants test, which, like I said, I came that close to being able to grade it yesterday. Just completely ran out of time. I even carried it home last night, but I had to go by the store on my way home last night, and that took longer than I thought. And I got home, and I thought I'd have some time to work on it. Just about the time I was starting to work on it, my wife came home. She was even later than I was. And then there were a whole bunch of stuff we needed to do, and I never got around to getting anything graded last night either. So I'm going to try to work on it today. I've got 2 hours this afternoon. I'm going to try to work on it then. So if you want to come by before 3:15, you can see if it's graded then. No guarantee, but I'll give it my best shot. Or tomorrow I'll be on Birmingham campus. If I don't have it graded by the end of the day today, I'll take it with me to Birmingham campus. I'll have it there so you can pick it up anytime tomorrow. And then Monday, anytime. I'll be in here. Let me go over this. I'll be in here doing a review session Monday from 8 to 9:40. No, 9:50. 9:50. But after that, I'll be grading in my office, or I'll go over that part a little bit later. So anytime Monday, you can come pick it up too, after 10 o'clock. Okay. Hopefully I'll have it graded. If not, I'll grade it on the spot and give it to you, okay, either today or tomorrow or Monday. Okay. All right. Then I guess the next thing is going over schedule. Today's schedule is irregular. This is still class week. So I have office hours today from 1:15 to 3:15. Tomorrow I'm on the Birmingham campus, 7:45 to 11:45. Now most Fridays I'll say, or sometime after 11:45, I don't hold myself to 11:45 on the nose. However, tomorrow I do have an appointment, I think at 1 o'clock, and I've got to get home, get lunch, and get there before 1 o'clock. So I'm going to have to leave pretty soon after 11:45 tomorrow. So that's one day I won't say, or, yeah, I'll be there a while longer. I may not. Okay. Okay, then let's go to next week. Next week is finals week. Throw out the schedule, okay? Times when I'm in class now, I won't be in class then. Times when I have office hours now, I won't be in the office then. Let me go over basically what next week is going to look like as best I can tell. Like I said, from 8 to 9:50, Monday morning, I'm going to be in this room doing a review session. So that's not a good time to come ask questions because I'm going to be working with that class. So if you have something just to turn in, just slide it under my door, my office door, okay? But after 10 o'clock or 9:50, 10 o'clock, then I'll be moving back toward the office. But, like I said, that's a review session, 8 to 9:50. What I'm giving that class is this option. They can either take the test at 8 o'clock, and if so, I'll get somebody else to proctor it, or they can come to the review session and take it anytime later in the week. Anytime later in the week. So therefore, I have to be open the rest of the week to give an exam anytime. So what I usually do when I'm in the office, which I should be after 10 o'clock, if someone comes to take an exam, then I find the closest classroom to my office, okay? For instance, 263, 256, 261, 259, 254. Any of those classrooms down there that are close to my office, if they're available, that's where I take them, and I do the exam in there. If those are all occupied, I make it on up here and either do 257, which is just next door here, or 255. I know this room will be open, but it's further from my office. And since I'll be grading papers from different classes, I'll be needing stuff from my office, going back and forth. So I just try to keep closer. Also, if I'm down there, sometimes I can hear my phone ring in my office. I can go pick it up because people calling from the outside don't know that it's final exams week and that I may not be in the office then, so I try to hang close to the phone. So, after 10 o'clock on Monday, it's either my office or some classroom in between my office and here, 265 to 255. All right. On Tuesday, I have an exam at 8 o'clock in the morning here in this classroom, 8 to 9:50. So I'll be here. If you want to bring something to me, I'll be in here grading papers, so you can bring it. However, if you have questions, that's probably not going to be the best time for questions because I'll be in here giving an exam. So again, after 10 o'clock on Tuesday will be fine too. By the way, what is Tuesday? Say again? Voting day. Very good. Don't forget to do that. Okay? And I've got to vote on my way in because I'm here till 8 o'clock on Tuesday evening. Polls will be closed then. So I have to vote at 7 in the morning and try to get here before my 8 o'clock final. So I'm going to do my best to get here. But my class knows about it. They're not going to leave. Okay? All right. But I think I'll be here before 8. Usually it won't take that long to vote, I hope. And if I don't have any traffic problems, I should get here. Okay. So that's Tuesday. So from 10 o'clock until 3:15, I should be in my office or some room in between my office and here. However, at 3:15, I've got a class because I have a second mini-term class. They have class next week. They're not just finals. They have a class. So I'll be in class from 3:15 in the afternoon until technically 7:45 that evening. Don't think it'll take us that long because all I have to do is finish the last chapter and do the last lab. So I'm guessing we'll be through by 5 or 6. I don't think it'll be 7:45. And I'll be here until 8 o'clock Tuesday night, but I doubt if I'll be in class until 7:45 because all we got to do is finish. Now here's something else I've done. I'm giving that class the option of taking the final early if they want to. It was scheduled for 3 o'clock on Thursday, but I'm giving them the option because some of them, more than half the class, are automotive students. And the automotive students, some of them are from out of state and some of them are from anywhere within the state. Mobile, anywhere. They come here for the automotive program. And because mine is their last final exam, I don't want them having to hang around up here for an extra 2 or 3 days. If they want to take their final early and go, they can. So I've given them that option as well. Now, all the students are automotive. Some of them may choose to take the final on Thursday. That's fine with me. I'll be here on Thursday to give it. But that's why I may be anywhere between my office and here giving a makeup exam any day of the week next week. Monday from 10 o'clock until Thursday at 8 o'clock in the evening. All right, so that's Tuesday. Wednesday, I have no scheduled final exams. So that means I'll be in the office from 7:45 until 5:15 unless I'm giving a makeup exam, and then those would be any classroom between my office, 265, and this room, 255. Anywhere in there I may be. Now, if you come by then and I'm not in any of those places, hang on. I may be at the registrar's office. I may be in the restroom. I may be at lunch. I'll be back really soon. So I'm not going anywhere except here. Okay. So that's Wednesday. Thursday, from 7:45 in the morning until 3 o'clock, anywhere, my office or any classroom between my office and here. 3 o'clock, though, is when the physical science class is supposed to have the final. I'm guessing a few of those students may choose to wait and take the final until Thursday. Fine with me. I'll be here. It won't take more than an hour, I don't think. So therefore, by 4 o'clock, I should be back in the office. Okay? Now, if I'm not, check out all the rooms in between. But I should be back in the office by 4 o'clock on Thursday. Okay, but I'll be on campus until 8 o'clock that night. Okay? Now, Friday of next week, I'll be back on Birmingham campus, 7:45 to 11:45. Now, grades normally are due by noon the following Monday, but occasionally they give us an extra day or two, so it could be noon Tuesday, or even noon Wednesday. I doubt if they'll extend it that far, but they could. The reason I'm telling you that, are you a regular Lawson student? You've been here a while, haven't you? Okay. You may have realized student suite goes down during finals week. Did you know that? Huh?
I don't really go on TV.
What's that?
I said I don't really go on TV.
Yeah, okay. We have an archaic system here, and the system only has something, at one time it was only 16 portals, okay? I think they may have expanded that a little. It may be up to 32, but still it's an awfully small number. And the first term that we tried this, none of us instructors could get into the portal to put our grades in because the students were all checking the grades. And when they were in, if they took up all 16, we couldn't get in. And so a lot more than 16 students that were trying to check the grades. So the students were griping that the grades weren't in, but the instructor couldn't get in the portal to put them in. So they finally decided they just had to shut students off of Student Suite during finals week. And they keep them off until grades are in, either Monday at noon, Tuesday at noon, possibly Wednesday at noon. As soon as grades are in, then students can go back on Student Suite. But the good news is, me and I think most other instructors, we put our grades on Blackboard. And then we put them on Student Suite anyway, or the suite anyway. So check Blackboard. Blackboard, like it would, never shuts down, It actually crashed either last spring or last summer, and that's when they gave us the extra day because Blackboard went down and that's where our grades were, But they, most of the time Blackboard is up, and you can always check your grades there because I enter them first there, and once I get them there, then I put them on Student Suite or on the suite. So, any questions on how we're going to wrap things up? Before you leave today, I did run down to to run off a copy of your test. I don't know how far we're going to get today, so we may not get all these questions covered, but I'll let you know how far to go. Okay. We're in Chapter 4. Let me just... Yeah, okay. We're in 4.3, and I think we got down to, on page 162, Theorem 4.5. Any questions before we get going? Okay. Theorem 4.5. Test for a subspace. Wait a minute. Did we even get started on subspaces? I don't think we did. I think we just finished 4.2. Because I don't remember talking about subspaces last time. Were you here? I can't remember. Tuesday? Okay, did we start on subspaces? I don't think we did. Okay, so let's start at 4.3. What in the world is a subspace? Okay? Now, a couple of concepts here. First, let's go way back to the concept of a set. What is a set? It's a collection of objects. Okay? It could be anything. Desk, it could be anything. In linear algebra, it's usually some mathematical entity. It could be a vector, a set of vectors. It could be a set of numbers, but not in linear algebra. Usually it's not that. It could be a set of matrices. It could be a set of polynomials. It could be a set of continuous functions. Any of those are sets. Okay? Now 4.2 talked about what a space was, a vector space. And a vector space is a set that follows those certain rules. Remember those 10 rules that they had to follow, right? And if they met all 10 criteria, it was a space. Always was a set, but if it fit all those 10 criteria, then we called it a space. All right. Back up a little. A set is a collection of things. A subset would then be a smaller collection of those same things. For instance, if the set of desk in this classroom was our space. Well, not really a space, but let's say it was. Then I could say a subset of that was those that had blue seats. Well, that would be that one and that one, okay? Or red seats, that one, and that, you know. So, and that, yeah. All the ones, yeah. That would be a subset of all the desks in the room, okay? So, let's go back to spaces. It's a set of things. The things could be vectors, matrices, polynomials, continuous functions, maybe some other things. But those would be, now, if they fit the 10 criteria, those are called a space. Now, if it didn't fit the criteria, it's still a set, and then you can have a subset of that. Okay. Well, let's say we did have a space of vectors or polynomials or matrices or something. It met those 10 criteria. Well, what is a subspace of that space? Well, it's a subset of that set, okay? So all those things that filled the first space, that's a subset of that. But to be a subspace, it has to have something else. So here's the definition of a subspace. In many applications of linear algebra, vector spaces, which we just talked about, and they don't have to be vectors. Remember, they could be matrices or polynomials or continuous functions or whatever, okay? Vector spaces occur as subspaces of larger spaces, okay? For instance, we'll see that the solution set of a homogeneous system of linear equations in n variables is a subset of Rn, okay? Blah, blah. A non-empty subset of a vector space is a subspace when it is a vector space with the same operations defined as the original vector space as stated in the definition. So here's the definition of a subspace, okay? A non-empty, okay, a non-empty subset W of a vector space, Vs is vector space V, is a subspace. It's always a subset, but it's called a subspace when this W, that subset W, is also a vector space. With the same operations of scalar addition and scalar multiplication. Okay, so here's an example. Okay, there's your formal definition. Okay, to move on? Okay, I'm going to erase this so I'll have room enough. Here is a set. The set is W, and it's the set of all R3 vectors that would be of this form. x1, 0, x3. Okay? Such that x1 and x3 are any real numbers. Okay? R1 and x1 and x3 are any real numbers. That's a set. Okay? That curly brace there, that's the set notation. This is a set of all three-dimensional vectors, x1, 0, x3. Okay? Now, what we need to show is that that is also a subspace. Subspace of R3. Okay. With standard operations. Now, what do we mean R3? Any three-dimensional vectors, x1, x2, x3. Any three-dimensional vector, the x1, x2, and x3 are all real numbers. That's a space. It's a vector space, R3. Okay? This is certainly a subset of that because it has all the x1s and x3s that that one did, only it has no x2s. Okay, now if you're x1, that represents goodness, I can't think what you call that. Coordinate, okay, that coordinate. X2 is this coordinate, x3 is that coordinate. Then this one would be everywhere the x2 is 0. So that would be that plane. Every vector in the plane that's x1, x3. That plane. Certainly a subset of the whole space, but it's just the vectors in the plane. They're three-dimensional vectors, but their middle dimension is always 0. Okay, so you're always in the plane. Okay. Now, the standard operations are adding two vectors together, you add all the components. Okay, you know that. And vector multiplication or scalar multiplication, multiply any scalar by it, you get a vector in that space. Okay. Now, is this a subspace? That's the question. We know it's a subset of that one. Is it also a subspace? Well, if you add any of these two vectors together, that would be x1 plus y1, 0 plus 0, x3 plus y3. Well, yeah, that's still going to be in that same space, isn't it? Because it still has 0 as that middle coordinate. So every vector you add in this R2 here, okay, is also going to be in R2. So that works. Vector addition works. Scalar multiplication works because if you multiply this by any number C, any real number C, this would be Cx1, comma, C0, which is still 0, Cx3. That's a real number. So those are all in that space. So vector addition works, and scalar multiplication works, and all the others. The 0 vector is certainly there. 0, 0, 0 is certainly in that. Okay? The identity vector. Everything works. So yeah, that is a subspace. For it to be a subspace, it must be a vector space itself. And that fits all 10 criteria for the vector spaces. So that's what we had to do to show that. Okay? Visually, it's this wall over here. Of course, that wall extends all the way past the hospital and all the way into Tennessee. I mean, wherever it is, it's there. Okay? Now, to establish that set W, or any set W like that, is a vector space, you must verify all 10 vector space axioms. Remember those 10, the big 10? We saw several different situations with them. If W is a non-empty subset of a larger vector space V, and the operation defined on W is the same as they defined on V, however, then most of the 10 properties are inherited from the larger space. You don't have to go back and prove all 10, okay? And need no verification. This next theorem states what you do need to do. If it's sufficient to test for closure in order to establish a non-empty subset as a vector space. So here's all we have to do. I think we can write this down here. This is theorem 4.5. If W is a non-empty subset of vector space V, same way we started out before, then W is a subspace, okay, of V, if and only if, that's the double arrow here, if and only if the following closure conditions hold. Okay? First, if U and V are both in W, then the sum of U plus V is also in W. Okay. Now, time out a moment here. Okay. Now, I talked about this before, but I want to re-emphasize it now. Just because I'm writing that's UV with a vector symbol over it, that doesn't mean directed line segment anymore. That U and that V could be matrices, they could be polynomials, they could be whatever vector that was in that vector space. Remember, our definition of vector is extended beyond a directed line segment. It can be continuous function. Yeah, it could be just about anything. Okay, not anything. So, the sum of those two, if both of those are in W, then the sum has to also be in W. So that's one closure. Secondly, and this is so simple, if U is in W, okay, and C is any real number, okay, actually they say scalar, which means real number. I'll put the same terminology down. Then CU is also in W. Okay? Now, again, remember U isn't necessarily a vector in the old sense. It could be a matrix, all those other things that it could be. And you multiply that by some scalar C, whether it's a function or a matrix or whatever it is, then that scalar product of C and that whatever vector U that was will also be in W. So if those two conditions are met, you don't have to do all 10. The other 8 all fit if W is a subset of V, then all those others are going to work. Okay? Perfect attendance our last day of class. That's excellent to see. And my question is, have you done the student course evaluation? All right, 100%. Okay? My first class to have 100%. Of course, it's my smallest class. All right, good to see. Thank you. The dean's all over us about that. So she wanted at least 80%. We got 100. Okay. Of course, if we only had one of you that do 50%, we fail. Okay. So, glad you did it. Number 2, have I returned your first 2 tests to you? Okay, I don't think I got your 3rd test yet, do I?
I'm sad about you.
Okay, that'll be fine. All right. Let's see, what was the other thing I said? All right, before you leave today, be sure you pick up the last chapter test. That'll be on chapter 4. Now, I made it up, not knowing how far we're going to get. So at the end of the day, I'll tell you, okay, do the first 15 questions. No, it won't be that many. 9 questions, 8 questions, 10 questions, whatever. Okay, I'll exclude any we didn't get to cover today. I know there'll be some of those. I just didn't know ahead of time how far we would get. All right, so I wanted to be safer rather than sorrier. Okay. Now, here we have a strange situation. This is always strange. Because a subspace of a vector space is also a vector space. If it's got space in it, it's got to be a vector space, okay? It must contain the 0 vector. Now that one we did up there, sure, it contains the 0 vector. x1, 0, x3, because x1 and x3 could both be zeros. However, if you did W to be x1, 1, and x3, that doesn't contain the 0 vector. So that would not be a vector space. It would be a subset, but it wouldn't be a subspace. Now, to get the idea of that, if you came 1 unit out y right? Your next axis. The plane that would be here, in fact, let's do this one. Let's imagine this is when y is equal to 0, you're on this plane. When you're on this plane, the one that connects that wall with this wall, then you're at y is equal to 1, right? Well, that doesn't contain the 0 vector. This one contains the 0 vector. 0, 0, 0 is on there. This one here contains 0, 1, 0, but not 0, 0, 0. So you've got to contain the 0 vector to be a subspace. The simplest subspace of any vector space V is the one consisting only of the 0 vector. Okay? That's always a subspace too. Because you add two 0 vectors together, you get the 0 vector. Okay? It's closed. If you multiply any scalar C by the 0 vector, you still got the 0 vector. That's closed as well. Okay? That is called the 0 subspace. That's all that's in it. You've got a space, a vector space, a subspace. It's just not very interesting. You got it. And every vector space contains those true trivial subspaces. All right, sorry. Another subspace of V is V itself. So if your space was R3, every point in space, okay, a subspace of that is R3, every point in space, okay? It contains all that, but also another subspace would be 0, 0, 0, which contains only that nebulous little 0 vector. And that's all there's there. Another subspace, okay, every vector space contains those two trivial subspaces, and subspaces other than those two are called proper or non-trivial subspaces. Like that is a proper subspace. 0, 0, 0 would be a trivial subspace, and x1, x2, x3 would be the entire space. So that would be trivial as well. So let's look at example 2. I snuck down to my office and ate me a little something, drank me a little something, but it's now worn off. Goodness gracious, I'm starving. Okay, but we can make it 20 more minutes. So let's look at a subspace of M22. Now what does that designation mean? M2, 2. What is that? Capital M stands for, it's one of the first things we did in this course early on. Started with M. Matrices. That's a matrix, and guess what size it is? 2 by 2. That's what that stands for. So let W be a set of all all 2 by 2 symmetric matrices. Okay, they have to be symmetric matrices. Do you remember the definition of a symmetric matrix? Either of you?
All the time.
What a symmetric matrix is. Okay? Two things specifically. Number one, it's got to be square. A 3 by 2, a 2 by 3, a 7 by 15, those can't be symmetric matrices. Okay? So it's got to be square. So 2 by 2, M22 is a square matrix. So that may or may not be a symmetric matrix. So there's one thing, it has to be square. The second thing, doesn't matter what's on the diagonal of that matrix. the main diagonal goes from upper left to lower right. Doesn't matter what's there, but the things here have to correspond to each other. Whatever 2, 1 is, 1, 2's got to be the same. Whatever 3, 1 is, 1, 3's got to be the same. So the 4, 7 has to be the same as 7, 4. Okay? So that's what is meant by a symmetric matrix. The diagonal, it can be anything it wants to, but anything off the diagonal has to correspond to what's across the diagonal from it. Okay. Okay. So here, W is a set of all 2 by 2 symmetric matrices. Show that W is a subspace of the vector space M22. Show that W is a subspace of the vector space M22. Okay. Now, back when it was hot outside, this room would be so cold my head was locked up. Now that it's cold outside, it got so hot that my head is clocking up. I don't know what's going on here. Whoever is doing the energy management is not managing well. When it's hot outside, they have a 68 in here, which takes more energy to cool it. And when it's cold outside, they have a 72 in here, which takes more energy to heat it. And that's not how we do things at our house. When it's hot outside, we bump up the thermostat and wear fewer clothes. When it's cold outside, we drop the thermostat and put on more clothes, okay? And guess what? When it's cold outside, I wear heavier clothes. Y'all wear heavier clothes. Why have the room hotter than it would be in the summertime? It makes no sense. I need to gripe to someone other than you. Okay. All right. Oh, and here's the definition. Recall that a square matrix is symmetric when it is equal to its own transpose. That's the other way of saying it. Whatever is in the columns, when you change the columns for rows, you get the same thing. Okay? So, basically, from the previous theorem, all you have to show is that the matrix addition is closed and scalar multiplication is closed. Okay? Now, and this is a 2 by 2. These are pretty easy to do. I'll probably do more detail than otherwise. So this is a representative matrix. Okay? Let's call this D1 and D2. Those are the 2 diagonal elements. It doesn't matter what they are, right? Doesn't matter at all. The 2 non-diagonal elements, have to be the same. So let's call that N and N. That is a generic 2 by 2 symmetric matrix, right? So, W is a set of all those, okay? So let's say we have another one, and we'll call that E1, E2, OO. Well, let's not do O. PP, okay? Where that can be anything. Add these 2 together, and this gives you D1 plus E1, N plus P, N plus P, D2 plus E2. I'm sorry, I can't read my writing. E2. Okay? And guess what? That's also a symmetric matrix. It doesn't matter what the diagonal entries are, just any diagonal entries, these two have to be in there, and they still are. So any two symmetric, 2 by 2 symmetric matrices you add together, the sum is also going to be a 2 by 2 symmetric matrix. Okay? Now, let's take this generic one here and do C. Some number C times D1 in D2. That would be the matrix that CD1, Cn, Cn, C, D2. I'm sorry, I sort of lost it there for a moment. That hurts. All right. Well, guess what? Doesn't matter what the diagonal is. These two are the same. That's also a symmetric matrix. A 2 by 2 symmetric matrix. So, sure enough, matrix addition and scalar multiplication result in symmetric 2 by 2 symmetric matrices. That's all you have to show. Okay? They approach it a little bit differently, but that's basically the same thing. Now, they use the transpose characteristics of it, and that's true too. So, I think theirs are a little more involved than mine. Mine's, I don't know. You can do it either way. All right, let's move on to example 3. Set of singular matrices is not a subspace of M in N. Okay, that's what it claims here. Let's let, what? Okay, let W be the set of singular matrices of order 2. Order 2. I can hardly read my writing. Okay? Now, it says show it's not a subspace of M22. Okay. Now, we have to remind ourselves, what do we mean by singular matrix? Anyone recall what a singular matrix is? No, any size matrix can be singular. Okay? Has what?
A determinant.
Still couldn't hear it.
A determinant.
A determinant? Okay. Okay, you're close. It has a determinant of 0. The non-singular matrix has a non-zero determinant. A singular matrix has a determinant of 0. Okay? That's a real concise answer. Okay? Let's see what they showed. And I was going to tell you something else, okay? Your answer was absolutely right. A determinant of 0 is a singular matrix. Here's another singular matrix. Any matrix who has a row of all zeros, okay? Or a column of all zeros too, but we're going to stay with rows. So therefore, here is a matrix. Okay, a singular matrix, 1, 0, 0, 0. That's a singular matrix. Number 1, what is its determinant? 0. Okay, so that's a singular matrix. Okay, now, if that singular matrix is multiplied by a scalar, C, it's also a singular matrix. Okay? And 0, 0, 0, 0, the 0 matrix is a singular matrix too. Both rows are 0. Okay. But okay. This is a matrix A. It's singular. Now notice here, W is the set of all singular matrices. Okay? That WB, I wrote it down wrong, a set of all singular matrices of order 2. Be a set of all singular matrices. Okay. Ooh, yuck. Set of all singular matrices of order 2. Well, here's another matrix that's a singular matrix. Remember, it can have, just needs a row of zeros. 0, 0, 0, 1. That's a singular matrix too, isn't it? Its determinant is 0. Okay? What happens if you add those two together? What's that? 1, 0, 0, 1. You got it. Is that a singular matrix? No, its determinant is not 0. 1 minus 0. In fact, that's the identity matrix. Not singular. So you see, if W is a set of all singular matrices of order 2, those are two matrices that must be in it because both of those are singular matrices of order 2. But when you add them together, you don't get something. So therefore, that's not a subspace. Subset for sure, but not a subspace because it has to pass that. All right. All right, let's do, if I can breathe long enough, example 4. Man, I need something to drink really badly. Let me just hold on for 6 more minutes. I think I can make it without choking to death. Here is a W. W is equal to the set of all ordered pairs x1, x2, such that x1 is greater than or equal to 0, and x2 is greater than or equal to 0. Okay. I can't get my pen to write. There we go. Oops. Greater than or equal to 0. Okay. Now it has standard operations. Okay. Is that a subspace of R2? Well, this part looks like it should be a subspace of R2, right? I mean, it's a subset of R2. So that's exactly how you define R2, set of all, or need to close my set notation there. Set of all x1, x2, when x1 and x2 are any real numbers, that is the definition of R2. But now we're changing this to be x1 is not all real numbers, but only positive real numbers. And x2, only non-negative real numbers. You can't count 0 too. So surely the 0 vector is included because it can be 0, that can be 0, that's fine. And when you add these two together, any two with all positive numbers, add them together, you're going to have all positive numbers. Yes. Okay, that works fine. But remember what your standard operation is for scalar multiplication. If you multiply by any real number c, you must be in this too. Guess what? What if you multiply by minus 1? Then this would be a minus x1 minus x2. That would not be in this set. So scalar multiplication would not work in this one, the way we define it. Now, if you change your scalar multiplication and say is for only positive c's that would work, yeah, then this would be okay. But for the standard scalar multiplication, no. So that one would not work. Okay. It's non-empty. It's closed under addition, but it's not closed under scalar multiplication because you multiply by any negative number, you take it out of that domain. All right. Let's try to get this one more in here. Okay. I'm going to start with a new slide here, even though there's not much on that one. Okay. We're going to look at subspaces of functions, and this is sort of a calculus type definition. Let's let our W5 be the vector space of all functions defined on 0, 1. Okay? Now, that's a lot of functions, okay? Can you think of any functions that it would not include? It says all functions. Can that be every function in the world? No, I can give you one that can. 1 over x, the reciprocal function. Very simple function, not defined on x equals 0, right? You can't divide that. Or 1 over x minus 1. You can't divide by 0 on the other end either, okay? In fact, you can't have one over anything in there. Another one that can't be on there. The log function. You can take the log of 1, you can take the log of 0.5, you can take the log of 0.9, you can take the log of 0.1, you can't take the log of 0. Not defined. So there are some functions that would not be defined here. Okay? But W is going to be a vector space, W5 is going to be a vector space of all functions that are defined on 0 to 1. Okay? Now, let's let W1 be defined this way. Set of all polynomial functions defined on 0, 1. Okay, guess what? That would be every polynomial function, period, ever. Because all of them are found everywhere, certainly at 0 to 1. So that's W1, set of all polynomial functions. Okay? They would also be a subset of W5, because W5 is all functions defined on 0, 1. So the polynomial would be there. W2 is a set of all functions differentiable on 0, 1. Okay, well, certainly all polynomial functions are differentiable, so W1 would be a subset and also a subspace of W2, but not all W2s would be in W1 because differential function, sine function, is not a polynomial function, and yet it's differentiable on 0 to 1. In fact, it's differentiable everywhere, but it's not a polynomial function. Okay, how about W3? W3 is a set of all functions that are continuous on 0, 1. Okay? All functions that are continuous on 0, 1. Well, certainly all functions that are differentiable are continuous. Know that. Okay? But are all continuous functions differentiable? No, not quite. Absolute value function is continuous, but it's not differentiable. Okay? So, this is a bigger group than that is. This is a bigger group than that is. Okay? So, that's W3. How about W4? Set of all functions are integrable on 0, 1. Set of all functions integrable on 0, 1. Okay? Now what does it take to be integrable? You can certainly integrate underneath the absolute value function, so certainly all those will work. I can't think right now. I know there must be some that would be integrable, but not necessarily okay, you finish? Okay. Actually, my class is over now. Are you on to take the second test now? Okay. We got to end. I didn't realize we just ended. I don't have it up here. I have it down in my office. So let me just give them their final exam. By the way, each of these is a subspace of, the biggest is W5, W4 is a subspace of that, W3 is a subspace of that. They're all subspaces. Not all, they don't go the other way, but they do go that way. And that's all we have time for. Okay? So let me give you, enjoyed having y'all in class. Let me give you your third test. And let's see what we got to. I didn't know how far we would get today. I know we didn't get to number 9, but we didn't talk about null spaces. We didn't talk about basics, so we didn't do number 8. We didn't talk about spans, so we didn't get to 7. We did get 5 and 6. So you can go through 6. If you want to try 7, 8, and 9, you can. If you get them wrong, they don't count against you. If you leave them blank, they don't count against you. If you get them right, you get bonus points. So do 1 through 6. Pretty easy final. Okay? All right. Sorry about that. All right. Good deal. Glad you both made it today.